All right, in this experiment, we're going to do a titration. This is where we start looking more at stoichiometry and reaction ratios. Specifically, we're looking at acids and bases. In the next two labs, we're going to be looking at the titration of an unknown sodium hydroxide solution. So this is actually a good opportunity to show you how to make a standard solution that can be used in this way. And standard solutions are made very specifically using this piece of equipment right here. It's called a volumetric flask. Volumetric flasks, believe it or not, are probably the most precise piece of glassware in the lab. When you look at the accuracy of these things or the precision of these, we're usually looking at, see here, the volume is 500 mils and it's plus or minus 0.2 mils. So that means it's within 0.2 mils of 500 mil. That's a very small percentage error in the reading, but the downside is you can only read 500 mils. You can't read in between like you can on a graduated flask, or very imprecisely like you can on a beaker. If you look, it's kind of hard to see, but if you look right at the bottom of my thumb there is a line scored into the volumetric flask. That is the 500 mil line. So when we make standard solutions, we use this instrument and we know that that's 500 mils. So whatever we put in here, we can then very carefully calculate the exact concentration. So we need an unknown system. So I'm not going to tell you how much sodium hydroxide I'm adding, but I have pre-weighed some sodium hydroxide here. We need to use it soon because sodium hydroxide does absorb moisture from the air, so we don't want it sitting around too long. But what we're going to do when you make a standard solution, first of all, you fill, we're using deionized water here, but we're going to fill about 1/3 to halfway up the bulb with the deionized water. That way when we add the solid, it doesn't just stick to the bottom. And then we're going to very carefully add our sodium hydroxide to this system. And we're just going to turn our little weigh boat here into the funnel to add. And all of it has added. We can kind of swirl it around a little bit so it starts to dissolve. So far we really haven't done anything with this solution of any great precision outside of the weighing of the sodium hydroxide. But now here's the important part. When you read how to make a standard solution, one of the phrases you might hear is fill to the mark or fill to the line. And what we mean by that is the reason we add the solid first is because then we're going to fill this liquid level up to that very precise line on our volumetric flask. And the reason we do it that way is because obviously the sodium hydroxide itself in this case has a certain amount of volume. So if I measured out 500 mils of water and then added my sodium hydroxide, I would technically have more than 500 mils of solution. So we'd have to go back and recalculate a lot of things. By creating our solution this way, we actually create a very precise 500 mils of solution with a very precise known mass of material in it. So I'm just going to label this sodium hydroxide so I know what it is. And I'm just going to put question mark molarity underneath because we don't know what that is. And we're going to try and dissolve in that sodium hydroxide. But now what we're also going to do is we're going to fill to the line with the deionized water so that we can now finish making our solution. Obviously, the more water we have in there, the faster that sodium hydroxide will dissolve. I'm just going to pause a little bit here. I like to be able to swirl that freely in order to get that to dissolve a little faster. Sodium hydroxide dissolves pretty efficiently, so it shouldn't take too long for those little pellets to completely dissolve. And once they've completely dissolved and we've filled to the line, we'll have our unknown solution. Like I said, I'm not going to tell you because we're going to use this unknown solution to determine the unknown concentration using titration. And that's going to be what we're going to do over the next couple of labs. So we're going to use this. That's why I'm making a good quantity of it. So we have plenty to use in case we need to do numerous trials or repeat the titration for any particular reason. We want to make sure we have enough of our standard solution that we don't undo all the good work we're doing. So we're just going to check and see if that's sitting on the line. It is exactly on the line. We can hopefully zoom in so you can see a little better here. We're actually maybe a drop below the line. So we're just going to use a clean dropping pipette to add a couple of drops to this to just get it exactly on the line. We might be about a drop or two below. Now we're right on the line. So now we have filled to the mark. So we have exactly 500 mils in there with the water and the sodium hydroxide volumes combined. And that's the important point, to make sure we get a good, consistent, standard solution. And we'll cap it. That way we can make sure we don't lose any water out of the system, so we don't get any evaporation or change in the concentration. You can see at the bottom, there's still a few little pellets back at the bottom that need to dissolve. So we're going to give it a couple minutes to take care of that, and then we'll be able to use that in our experiments. And that's how you make a standard solution for any lab or any solution. All right, in order to do the KHP, or the potassium hydrogen phthalate titration, the first thing we need to do is we're going to measure out 2 quantities of KHP. That's just the abbreviation for the potassium biphthalate or the potassium hydrogen phthalate. And what we're going to do is, obviously, we're just going to turn our scales on. We're going to let them go through their equilibration. While that's equilibrating, we're going to get what we need. So we've got 2 little pieces of filter paper that we're going to use for the weigh boats, and we have potassium hydrogen phthalate itself. So now it's ready. We're going to open it up. We'll zero it. We'll weigh our filter paper. Now you can do this in one of 2 ways. You can weigh the filter paper, put it on, and come back and weigh it later to get a very precise amount of the hydrogen phthalate. Given that this top hand balance only actually goes to hundredths of a gram, we don't need to be that precise here. So what we're going to do is we're actually just going to zero this out. And we're going to weigh somewhere between 1 and 1.2 grams of the hydrogen phthalate. So we're just going to carefully measure this out. So we're going to be sort of in the middle of that range. So the first one we have that mass. So I'm just going to call this one A, so you have your reading. I'm going to call that one A. That's how much is going to go into A. Now what we're going to do is we're going to weigh out a second one. We're going to zero that. And then we're going to add approximately the same quantity. Okay, so a slightly different amount. We're going to let the balance settle. And that's the quantity that we have on the second one, which we're going to label B. So take your reading, and we're just going to label this as B. And that will go into our second Erlenmeyer when we get to that part of the experiment. All right, so in the first step of this titration with the KHP, we've got our 2 weighed samples that we have right here. And the first thing we want to do is we want to label our 2 Erlenmeyers, A and B, so that we know where those 2 masses are going. And then what we're going to do is we're going to pour carefully our A and our B into those 2 Erlenmeyers, and we're going to try and get it straight to the bottom and not down the sides if possible. And if you just give it a very gentle flick, you can kind of get any remnants off it. And then we're going to do the same for B. Alright, so now we've added our KHP into Erlenmeyer's A and B. We have the start and instructions. Really here we want to be adding about 30 mils of water just to give ourselves a reasonable concentration. Now we don't need to know exactly how much water. We're not trying to determine the concentration of this system. We want to try and determine the concentration of this unknown sodium hydroxide. So long as we know the amount of KHP in here, we're good. So we're going to add about 30 mils to each. You could get a measuring cylinder and measure out 30 mils and put it in. That would be a fairly precise way of doing it, but we don't need to do that. Instead, we can just use the marking on the Erlenmeyer in this case. So we have a 50 mil marking here, so we're going to measure up to about 2/3 the way up to that, so that we have approximately 30 mils. And we're going to rinse down the sides just in case some KHP got stuck on there on the way down. And we can kind of swirl it around just a little bit, and then we're going to fill it to about 30 mils, like I said. So that'll be about right there. And then we're going to do the same for B. So we're going to try rinsing around the sides first, just to wash down anything that might be on the sides. And then we're simply going to fill to about 30 mils, so about 2/3 of the way up to that 50. We'll put us around that 30 mil mark. So that should be good right about there. We'll give it just a little swirl to help some of that KHP dissolve in. And you can see those two are actually pretty equal. So now we've set up our KHP system, we're ready to actually start titrating the NaOH. But in order to do that, we've got to have the equipment set up. So we're just going to push these out of the way so that nothing happens to them. And in order to do our titration, we need to use something called a Buret. And a Buret is a very long, thin piece of glassware. We'll zoom out so you can see a little better. See how long this is. It's about 3.5 feet long. And if you look closely at it, you can see that it's got very precise gradations the whole way up. So it's just like a very long, thin measuring cylinder. So you can see there are 10 markings between each mil, so you can figure out what each marking represents. So how do we put this in a way that we can use it? How do we build it? So what we do is we use a stand like we have done for the ring stands and the clamp stands. There's two ways that you can clamp a Buret onto this. You can use a standard clamp. If you do that, what you'll basically do is you'll put the clamp on the stand, and then you'll just carefully have the Buret in there and you just clamp it shut. So you would put it in the teeth of the clamp and basically just clamp that shut. If you have access to Buret holders that look like this, these are a better way of doing it. These spring clamps on the side, you just squeeze those down, the Buret feeds between the two, and then it'll just clamp down very gently or with the right pressure that it won't break your Buret. Now, this Buret's made of plastic. A lot of these are actually made of glass, and they're very expensive because, well, they're fairly precise instruments and they're made of glass. So when we use these, we want to try not to break them. So we're just going to slide this down the pole like we would if it were a clamp or a ring stand. It just clamps onto the stand. And then we're simply going to squeeze one of these clamps here, and we just carefully place the Buret in the middle of these little runners on the side. So now what we have is we have our Buret clamped in here, and if we want to release it, we just hold the Buret and we just pinch these down to release it. So it's a very simple way of actually holding these Buret stands. When you're handling a Buret, one of the key things you want to be careful of is the tip at the bottom. That tip at the bottom, especially when it's made of glass, is very easy. These are very long pieces of glassware, and it's very easy to just turn around or move it quickly and not be focused on how long it is, and you just catch the end of this and it chips or breaks. The moment this tip here is chipped or broken, you can assume that there's a certain degree of inaccuracy or imprecision in your measurements, so be careful with that. with this burette when you have it. Now, once we have our burette set up, we then need to be able to use it. To do that, we need to be able to fill it and clean it. So you should clean it first of all with at least a few mils of deionized water. I've already rinsed this one with deionized water. But then what you also want to do is you want to rinse it with the material you're going to use for the experiment itself or for the titration itself. One of the important aspects of this is the following. This tip down here is like headspace. So if there's any air or in there when you go to do your measurement, if this isn't filled with your liquid, then you are not going to get a precise measurement by looking at the difference on this burette stand. So we first of all need to fill this with our system, and then we need to drain it so that we can make sure that that headspace is indeed filled with liquid. So we're going to do that now. I'm going to just pause this here, and I'm going to rearrange this so you can see exactly how we should be filling this. All right, so when we're filling our burette, the most important thing is that we're filling it at eye level. You'll notice I've moved it out of the hood just temporarily here. I've sat it on a stool. The reason being, when I do that, this is now at a filling eye level for me. So when we're filling this, we want to be filling it at eye level. But before we do any filling, one of the first things we want to do is we want to make sure that the burette is closed. If you look at the base of the burette, you'll see there's a little orange stopcock handle on the right-hand side here. When it is vertical like this, that means the hole is open. That means water is going to go this direction. When we turn it 90 degrees to that, so now it's running horizontal, now the stopcock is closed. So before you put anything in there, you should put that horizontal like that to make sure that nothing comes out, so that when you fill, it doesn't just come pouring at the bottom. If you want to be super cautious, it's not a bad idea before you do any filling to put a beaker or an Erlenmeyer underneath this tip, just in case anything leaks out. Sometimes these stopcocks are not in tight and they leak, and you don't want it going everywhere. So just to be cautious, we're going to do that. We're simply going to put a small Erlenmeyer just underneath that. Notice how it just goes underneath the tip. I've made sure it's closed, but just as I fill, I just want to make sure that if anything does leak, I'm going to be able to catch that and not have a big mess to clean up. And then we're going to go back to the filling of the Erlenmeyer. So I'm going to give you a better view by moving you up here. When we fill the Erlenmeyer, we want to make sure that we're using a funnel. So we're just simply going to use a small thin-necked funnel. I'm going to put that on top. We're going to grab our unknown sodium hydroxide, and we're going to use this to fill. And as we do this, initially we're just going to make sure that nothing comes out the bottom. And I'm not seeing any leaking, so we're good. So I'm just going to fill this about halfway. So this is a 50 ml burette. I'm going to put about 25 mils in there. So as you can see, it's filled to about the halfway point. And then what I'm going to do is at the bottom of the burette, we're now going to open and drain the tip. Remember, the tip right now has only air in it, which is no use to us. We need to have liquid in there. So in here, so we're going to bring you in closer so you can see this more clearly. So in this tip right here, right now, we have only air. So we're just going to turn our stopcock vertical, and you're going to see the liquid comes out. And we're going to drain out about 20 mils or so, just to make sure that tip has been nicely rinsed out with the material that we're actually going to use. Now we have a liquid level in here, which is what would be in there if it's full of our material, so we're going to use that as it is. We've now rinsed this out. We're going to leave the Erlenmeyer there for the moment, and we're going to go back and we're going to now fill this towards the top. Now when you fill a burette, you don't have to fill it all the way up. It's actually okay to just fill it towards the top. So I'm going to fill this burette probably to around about the 2 or 3 mil mark. We're not going to take it all the way up to the 0. There's nothing wrong with taking it to the 0. You just want to make sure it's fairly full so you have enough to do your titration, hopefully in one go. If you overfill it, then you need to drain it out so you start at a known marking, because effectively when you do a titration, you're going to start with an initial reading and a final reading. And so as you do this, you want to make sure those readings are legitimate. If you happen to go above the 0, then you're not going to have a good initial reading. So that one is just below the 0, so we're good. We're going to pull our funnel out, because what we don't want is maybe a stray drip to come out of that while we're taking our measurements. And we have now successfully prepared our Buret for use. So we're now going to move that back into the hood. I'm going to remove the Erlenmeyer and just carefully move that back into our hood so it's ready for use. Put our Erlenmeyer to the side that has our waste in it, and then we're going to prepare to do our titration. Alright, so in order to start the titration, we have cleaned our Buret. We have also added it to our stand along with the stand clamp. Notice the bottom we have our stopcock is closed. We have everything else we need for this too. What we're going to do now is we're actually going to start moving through this experiment. We're going to take our unknown A and we're going to add some phenolphthalein indicator to it, and then we're going to start draining the stopcock, and I'm going to show you how the operation of the Buret, so that we can do this correctly. So we're going to move in a way that we can see the line move down. So the first thing we want to do is take our unknown A here. So this has the KHP already in it. As you can see, most of it's dissolved. Put on the black surface, you can see a bit, but there's still definitely a little bit in there. We're going to take our phenolphthalein, which is an indicator which will show as a change in pH. So that way we can find the endpoint. We're just going to add a few drops of this to the system. So we added about 6 drops. And we're going to cap our phenolphthalein because we don't want anything to happen to it. We're going to just give this a quick swirl to make sure everything is done and mixed in. We're going to put a piece of white paper underneath our Erlenmeyer so that way we can see changes in color that might come with this system. Now when we operate in a Buret, there's a couple ways to do it. It sort of depends on what your handedness is. If you are right-handed, usually what the recommended way of doing this is to actually operate the swirling of the Erlenmeyer with the dominant hand, and you will operate the actual Buret with your non-dominant hand, and you use this, kind of reach around, and you can use that to move it vertical and horizontal in order to let the sodium hydroxide out of the Buret. And while that's happening, you'll be swirling with the other hand. I'm actually just going to turn the base here a little bit to give me a little more room to swirl. So that way we can actually do this correctly. The first thing we need to do though is we need to get an accurate reading of our Buret. And it's going to be hard to do this from far away, so we're going to move this camera in really closely so we can see at eye level what that reading might be. So we're holding this at eye level, we're focusing on it. And from this, you should be able to get a suitable reading on the Buret. Now remember, when you read this, you do have a certain precision that you want to make sure you don't lose when you take these readings. If the system is sitting right on the line, so I'm going to read this to you. When I read this, I'm reading that as 0.30. So if it's sitting right on the line, you don't say 0.3. If it's right on the line, you know that last digit of precision is a 0, so you can say it's 0.30. If it was between the third and the fourth hash mark, then it would be 0.35, because you can estimate it as being halfway between the 3 and the 4, the 0.3 and the 0.4. So that one looks like it's sitting right on the third hash mark below the 0, which is 0.3. And since it's right on the line, our actual reading is 0.30 mils. And that's our initial reading for this titration. So what we're going to do is initially we're going to just start adding this at a reasonable pace such that we can swirl this system until we start to see a slight pink color. If you look carefully right at where the liquid is hitting, you might be able to see a pink color beginning to form. And so that's where there's a localized change in pH, but when we swirl it, that goes away. And what we're trying to do is we're trying to find a point where we start to see that pink be a bit more spread and be a bit more persistent. At that point we know we're getting close to the end point of this titration. And we don't know how much it's going to take, so we have to be vigilant. And occasionally we might want to pause it if we think we're getting close, and just to see if that pink color is more persistent. So we're sort of getting a little closer now, but it still goes away with a little swirl. See how it gets a very localized change in color where the pH has changed where the sodium hydroxide hits the solution, but if I swirl it, that goes away. So we're just going to let it come through at a reasonable pace so that we can start to see where that pink color, and what we're looking for is just a very faint pink color that is more persistent. So we're going to keep swirling and dropping this down, and we're not looking at the level of the liquid here. We just want to see whether or not this will actually turn. And that pink color seems to be becoming a bit more persistent, so we want to be careful now that we're getting close. See how it's getting much deeper. That's very close now. It's not going to take many more drops to get us there, so we're just going to let it add dropwise. And as soon as we see that change become persistent, we're going to close the stopcock so we can take our second or final reading. And we are fully there. One could argue we probably went a drop or two too far on that one. So we can now take our reading on this stopcock, on this Buret. So we're going to try and get you right at eye level here so you can get a good reading on that Buret. That should be a way to get a good reading. We'll move it around the other side to give you a second view. And that should be your final reading with sample A. So do your best to estimate the value of that Buret reading. Now what we're going to do is we're going to reset this whole setup, which means we're going to refill our sodium hydroxide solution, which means we're going to take it out of the hood to do that. I'm just going to do that off shot, but we're going to do exactly what we did before, where we filled it up towards the 0 mark. And once we've done that, I'm going to bring this back into sight so we can run the second titration. All right, so now we have our Buret conditioned for our second run. What we're going to do is we're going to try and get a good reading on that Buret again. So we're going to bring it in so that you can see it at eye level. All right, so there you go. You should be able to see that at eye level. What we're going to do now is we're going to start preparing our second sample B. So remember, the first thing we're going to do is we're going to add a couple of drops of phenolphthalein. There's still a little bit of undissolved KHP in there, but that will dissolve in as the reaction goes. We're just simply going to add a few drops of the phenolphthalein to this. So we're trying to set this up as similar as possible to the other reaction. We're just going to swirl that phenolphthalein in, and then we're going to set it up underneath our titration here. And then just like before, we're going to swirl and add. Now, the good thing is we actually have a good idea of how much we're going to add, so we don't have to be quite as careful this time. We can kind of let this drain through quite a bit, knowing that based on our prior reading that we can let quite a bit of this in before we need to worry too much about getting to that end point. So that makes the second and other runs after that a lot faster, because once you have an idea of that, it can make the whole process a lot faster. So you can see we're going to run this titration a lot quicker. We still want to be careful when we get into the last few mils to make sure that we are watching carefully for that endpoint. And we're going to try and get to a similar endpoint as we did before. So that way we know we're getting comparative data. And just be careful when you're doing this to try not to chip the tip of this Buret or break the tip off of it as you do this. When you get to that end point, it's going to come up on you pretty quickly, so I'm just going to be careful here. And then right as I say that, we hit the end point. So now we're going to compare A and B together, and I would say those endpoints are at pretty similar points. They're almost identical. So this is slightly rich. Really, a drop or two earlier probably would have been a bit more precise, but this is still a pretty good result. These two are very similar, and we are within a drop of that endpoint. So now what we're going to do is we're going to try and take the reading of that endpoint. So we're going to keep you at eye level here. Try and put something dark behind it so you can get a good reading. And we're going to zoom in at that point. Might be just a little high. Now you can get pretty good reading on that line. There. So we have our initial and our final for the two runs. So for this, you can now use stoichiometry and reaction calculations in order to find the concentration of our unknown sodium hydroxide solution.